to the Trinity College Open Day. I'm Vojislav Krisic. I'm working in the School of Physics. Oh, sorry, the left-hand side here seems to be cut off. I'm working in the School of Physics and principal investigator at the Center for Research on Adaptive Nanostructures and Nanodevices. And I'm going to present to you a little bit the area in which we're working in, how this is embedded into physics, give ideas about where would you find things like that also in your undergraduate course, and trying to show you that indeed small is different from that what you know in your daily life. A little bit about the School of Physics, even though you might have heard about it, it's still the strongest physics institution in Ireland with a lot of great physicists working here, and of course it is home of Ernest T. S. Walton, the only Irish physicist who ever won the Nobel Prize in Physics. And for me, since I came here something like 6 years ago, it still looks a little bit like Hogwarts with all these old buildings and the library, which is really fantastic, and I invite you to visit it there. Now, saying that, there's of course also a few modern buildings. This is the Center for Research on Adaptive Nanostructures and Nanodevices, and it's also the first and also largest institute in Ireland which is entirely dedicated to research in nanoscience, nanotechnology, but also, most importantly, in third level education, which means whatever is done in that institute spills over into the undergraduate curriculum in terms of lectures, special seminars, projects, and so forth. Now, nanotechnology, nanometer, nanoscience, nanomedicine, nanospintronics, nanoproducts, nanoelectronics, nanobots, and so forth and so forth. These are all words which you may have heard in the news at some stage or talking to people. And the big question is, what is it all about? And basically, you can start summarizing all that by looking at 3 words. Well, the first word is nano, which is a prefix which simply means small. It's derived from the Greek word nanos, and which has actually the meaning of dwarf, dwarfish, or little old man. It just means 1/1000th of something, right? Whatever you're looking at divided by 1 billion, that's approximately, that's where when you talk about nano systems. Now, what is nanoscience? Well, that's the part of science which focuses on these small things. And what I'm going to show you a little bit later is it goes beyond that. Things, as you know from school, in a classical sense, that there's physics, there's chemistry, there's biology. It's actually comprising all these features, and it's not that what you experience in your daily life. The third word is nanotechnology, right? And this is basically just the art and science to really address and look at things on a nanometer length scale. And to enable them, if you manipulate them, to do things which these materials or these objects, when they are so small, actually don't do when they're of bulk size, which means your daily life again, so on the meter size or kilometer size length scale. And actually, that's already ongoing, right? This nanotechnology is already on the market. People are buying it every day. Most of you have the smartphones which wouldn't exist without nanotechnology. But also in the chemical and pharmaceutical industry, it's used everywhere. In particular, if you buy sun cream, there you will find some nanotechnology inside. There are some nanoparticles inside. Simply, they are able to absorb better UV light than larger sized particles, right? All are already in use, actually very successful. Now, the big question still is, what is small? And let me take you on a journey to demonstrate that. So what you see here is a very beautiful bush of red roses, right? Which on that scale is approximately 1 meter. So going here from the, sorry, where is it? So going from the left of the image to the right, it's approximately 1 meter. Now, let's zoom a little bit in. Oops, sorry, wrong direction. So, about 1 order of magnitude, which means to 0.1 meter, 10 centimeters. And then you see that this bush is actually not just consisting of red and green blobs, but instead these green blobs are leaves which have some structure. And you even can see on this particular leaf, there is a fly sitting. Let's go one further. 1 centimeter, and then you look at the fly and you say, ooh, this fly is not just some little thing. It also has some structure. Here you can see the eyes, here the body, here the wings, tail, and so forth. Let's get closer. 1 millimeter. Well, if I had shown you this image first, and I would have asked you, what is this maybe, you would have said, maybe some exotic fruit, I don't know. But in the end, no, it's just the eye of the fly. So you get down, and things start to look already quite different than we would imagine with our eyes in first glance, at least on the meter scale. So if we go one more, at 0.0001 meter, so 10 to the minus 4 meters, this here is an electron microscope image of the eye of the fly. It's working basically like an optical microscope. The only difference is that you don't use light in order to image your object, but electrons, which means you shoot the electrons on the surface, they are backscattered, and you just collect the backscattered electrons, and you can process that by some software into an image. Now, this is now already, we're getting closer to this nanometer scale. We're not yet there. We're 5 orders of magnitude away. So let's go deeper. One more, 10 to the minus 5. So this is one of these antennae, which is at the junctions of each of these little, how do you call them, blobs? of the eye of the fly, right? Which are actually quite sensitive antennas, which help them not only to see, but also to navigate things. And then you can zoom in now 1 micrometer. That's actually where this antenna comes out, right? So here's the root. Now let's make a big jump by 3 orders of magnitude. And what we see is we are on a length scale which actually enables us to look at DNA, which is, as we all know, the main ingredient for life, right? And actually, the diameter of a DNA is typically around 2 nanometers, right? And here we are, 1 nanometer. So this is the length scale in which nanotechnology, nanoscience is working in. And to go one more, right? So just 1 order of magnitude more, so 0.1 nanometer, or called 1 angstrom, you start to see the individual atoms. And actually, as a rule of thumb, you can say 1 atom has approximately the size of 0.1 nanometers. Which means if you do nanoscience, nanotechnology, you're working on that level where you have to think about what are individual atoms doing, sometimes also clusters of these atoms or larger ensembles, and see what type of properties they have, and so forth. Now, in terms of these things being seen in the undergraduate curriculum, all this is, of course, discussed, and in particular, of course, the physics of all the different length scales which you have seen. So what is happening on the meter scale, and then you slowly go your way down, you will find quite a number of interesting things to happen. All that is done within lectures, small group tutorials, special seminars, and also laboratory work. Now, now we know what is small, fair enough, but why is it different? And bottom line is, physics at that small length scales, right, when you're in the nanometer scale, does not behave in the same way as you know it from your daily life. So in your daily life, which we can call the macroscopic world, basically, as I said before, you can divide something like between physics, chemistry, and biology. You can do some classical division. You can talk about classical mechanics, classical electrodynamics, organic, inorganic chemistry, and so forth, right? All that what you know actually already from school. Now, if you go to the microscopic or small world, which means you're on the nanoscale, things are different, right? You don't have this division anymore. And actually, I tend to call it simply, well, what you're doing then is science, generally speaking. And this area, this microscopic world, is entirely dominated by quantum physics, also sometimes called quantum mechanics, which was discovered and formulated by quite a number of important physicists: Max Planck, Erwin Schrödinger, Werner Heisenberg, Niels Bohr, and even Albert Einstein was contributing to the formulation of the laws of this small length scale. Now, because things are getting so small, you find different behavior. And let me demonstrate that on this very simple example here. So imagine yourself, so maybe today, or maybe you did it yesterday, or you did it a couple of years ago. This is yourself, you take somewhere a ball, soccer ball, and I hope that everybody of you has played already the game of taking the soccer ball and kicking it towards the wall. And what was typically happening was this. It was just bouncing back. And so you continue doing it, and all these kind of things, and having hopefully a lot of fun. Now, this is on the meter scale. So this is on the scale of your body size, if you want. Now think about yourself, the wall, and the ball, and you make yourself really, really, really small. So you shrink yourself. You shrink yourself to the size of a nanometer, say. Instead of being about 1 meter 70 to 2 meters, you're now 1.7 or 2 nanometers high. And now you start to play the same game, right? So you want to kick the ball against the wall, and you hope, oh, let's do the same thing again. So let's have a look what is going to happen. So you kick it, the ball hits the wall, but then something can happen which you do not see in your normal life when you're 1.6 to 2 meters tall. What can happen is indeed you kick the ball against this wall, and the ball is not going to bounce back. No. What the ball is going to do, it's going to go through the wall. It's a phenomenon which is called tunneling, right? So there is actually a certain probability when you kick that ball on that length scale, when you're that small nanometer scale, against a wall, that the ball is not coming back, right? And, well, if somebody ever has seen this happening on the macroscopic scale, which means you are about 1.6 to 2 meters high, please tell me. I would like to see that, right? So there's something strange happening if you are on these small scales. And this is what quantum physics or quantum mechanics is basically about, right? It explains why these things are behaving like that and so forth. And the cornerstones of that quantum physics and quantum mechanics is basically every object, which means also yourself, okay, is both at the same time. You have to regard yourself as something solid, but at the same time you're also a wave, which means you have all the properties of a wave, which you may know looking down Dublin Bay, Irish Sea, doing the same thing. That's a little bit weird at a first glance, and it takes some time to rationalize that. But because it has, if you look at objects and you accept that it has these properties to be as much a solid, as much as being a wave, quite some funny stuff can happen, as, for example, this tunneling effect. Now you would say, oh, is this of some academic interest or something? The answer is no. All your hard drives, which you have now in your computers and laptops and smartphones, etc., they all work because of this tunneling effect, right? So it has some real-world application. You just have to get small enough, okay? Another little thing which is associated with this quantum physics and quantum mechanics is the fact you cannot simply take an object, right, and simply divide it an infinite times, right? You're always going to end up at some certain limit where you can say, I cannot divide it anymore. That's the smallest piece I can make out of this. The word for that is the smallest quanta, right, or the quanta. And this is what is meant by this quantum or quantization, which you may have heard previously, but as I also have mentioned before. And the perfect example for that, which most of you already know, is the electric charge. So the electrons which are running around the nucleus in an atom, that's indeed the smallest charge quantum which is existing. You cannot get a smaller electrical charge, right? And so like this, there are many other objects which simply are confined by that. And this gives additional consequences with which you need to live if you're working on the nanometer scale and you want to do things and all this stuff. So all this has to happen when you are on that scale, 1 nanometer. Let me give you a few more examples. So nanoscience, studying and understanding of things or what they do if you look at them at the nanoscale. So a prominent example is graphite. This thing on the left-hand side is a pencil lead, which you all probably have used, and you have said, oh, I can write and draw things, everything is fine. Very easy to get, very cheap. On the right-hand side, graphite, which is made of carbon. On the right-hand side, you have a diamond. Not so easy to get, very expensive, and you can impress typically women a lot if you buy them one. The point is, the only difference between these two guys is carbon, right? It's carbon atoms. The only difference between these two guys is that you arrange the atoms in a different way. In one case, it looks dirty, grayish. In the other case, some brilliant, very nice material. Now, let's zoom into this pencil lead, right? With this electron microscope, which I was talking about before. And if you zoom in here on this tip, then you see this tip has actually some structure. Oh, okay, it's not just shiny gray, no, it has some structure. You zoom further in, and you see the structure there seems to be made of some flakes, right? And here is a sketch of these flakes. It's basically some sort of like sheets of carbon atoms. Each of these sheets consisting of an hexagonal lattice of carbon atoms, these black spots. And we can even nowadays look at these sheets, at single sheets, and image these carbon atoms. So what you see, this yellow, this bright spots is actually a single carbon atom, right? So there are techniques in order to observe that. There are also techniques to manipulate that. Now, what can you do once you have such a sheet? Well, you can look at the sheet itself, which is fine, not a major issue. But what you can do is you can roll it up into a little tube, right? If you do the proper things. And these tubes typically have diameters in the order of magnitude of 1 nanometers, maybe a couple more, right? Or you can make little balls out of it, like this fullerene or buckyball, right? Which, if you look here careful, you see here are hexagons, but there are also pentagons. And if you think back maybe a couple of years ago, the normal soccer balls always had black patches and white patches, right? And if you look at this fullerene or buckyball, then you will see, oh, these pentagons are actually exactly the same pentagons as on the soccer ball. So the soccer ball has already the same symmetry as this fullerene here. Of course, it's a much larger thing, but it's interesting from a symmetry point of view. Now, one thing which the soccer ball cannot do is, if you make it only on that size, right? How much? 20 to 30 centimeters diameter. If you try to make a soccer ball only with one atomic layer of atoms, this thing is going to collapse. It's energetically not stable. However, if you try to make a soccer ball on a nanometer scale, suddenly it becomes energetically stable. The same argument holds here for this carbon nanotube, which means things suddenly appear to be existing on a small scale, which you cannot observe on a large scale. And all these things have new properties which you can investigate and use, of course, for all types of applications, right? So there's, as I said, a couple of things you can do. We also know how to grow these structures. Here's another type of image of such a carbon nanotube. If you look careful, then you here see some fringes, which is actually following the atoms. Here, what you can see is, if you look careful, there's one carbon nanotube lying on some substrate, and on top of that, you have some electrodes. So we can even deposit metal locally on such nanostructures and measure, for example, their electrical response. What resistance do they have? Does this resistance change if we do something fancy to it? Or is the resistance in itself fancy? So we can use it for something, including all this tunneling effect. We can, of course, also look at some other structures, like here iron oxide and magnesium oxide, and look how, if we put the two things together, how the interface looks like. Here is a cobalt nanowire with an iron oxide layer around it, and here what we have is a germanium nanowire which is suspended over two electrodes, right? So there's a lot of technology involved in order to get there, and then to understand afterwards also what these new structures, which we are not know from our macroscopic world, are actually doing. Another example is, for example, if we take a metal, for example, nickel. And metals like gold, nickel, silver, platinum are very often used in jewelry, simply because they're so shiny and all this stuff. Some of them don't like to oxidate too fast, and so forth. And we can have them in many different forms. Now, what is happening actually if we take, for example, nickel, and we shape it on the nanometer scale, right? So this here is, sorry, you can't see it. It's cut off. It's 200 nanometer, this bar. So one of these structures is approximately 100 nanometers in diameter, right? And we structure it in these little coils, right? Here you have a magnification of that. So this here, the width of the wire which is making the coil is approximately 50 to 60 nanometers. Right? Here a little, on the left-hand side, some calculation on how such a structure would look like. Well, the question now is, will this structure, which is nanometer scaled, still be nice and shiny? And the answer is no. Actually, what you see here is an optical image, right? Which was taken by a simple camera, as you have it also at home. So what you see here, this shiny stuff outside, is a simple nickel film, right? So we just took nickel and we deposited on some substrate. And it has still this yellowish color, it's shiny, everything fine as we know. But these structures, if you look at them, that's this pitch black square here, right? So simply by making things small, right, even though we believe to know their properties on a macroscopic scale, on the scale as you are used to, we make them small, they suddenly change completely, right? And these gives in this case completely different optical properties, which is a source for new types of applications in solar energy, energy harvesting in general, which of course can go into all this smart technology, right? Again, all this is possible only if you're on a nanoscale, and of course you will get exposure to these type of things in your undergraduate level. For example, in the 4-year, 3-month project, summer student projects, of course, always, and even in 2nd year poster projects. So, finally, last word maybe on electronics. How did our society basically is based on electronics, right? Most achievements which you know from today, with which you're living when you go home and all this stuff, is because you have developments in electronics. How has all started off? Well, quite a while ago, it was microelectronics, which means everything was a micrometer scale, so 1/1,000,000th of a meter, right? And then companies started to make it even smaller and smaller because they said like, oh, hold on, if it's smaller, we need less material, therefore it's cheaper, we can sell it cheaper, and so forth. Things are getting faster, etc., etc. And so if you follow that line, it's very natural that at some stage you must end up in nanoelectronics. And this year I borrowed from a colleague who is working actually in Intel here in Lixlip, and he was telling me, okay, this is how Intel has developed its whole product range, right, from about 2003. And in around 2003, the single transistor which you have in your central processing unit, right, had already only a size of about 90 nanometers. So already 2003. And this year, or last year, beginning this year, they have launched a new one, which is the 22 nanometer, which is not here on the scale, but it's now that the transistor is even now 22 nanometers large. But they start to have all these problems with this effects with all this quantum physics phenomena, like tunneling, etc. So you need to do new tricks in order to keep things going. And if you look very careful, then this evolution is not mainly driven by the fact that the transistor concept has been changed, but actually more and more new materials, nanomaterials to be precise, come in, like nanowires or 3-5 semiconductor structures or carbon nanotubes, field effect transistor, right? So there's a clear motivation from industry, yes, we need that, right? This is now electronics, but the same is valid also for biotech, energy, pharmaceuticals, chemistry, whole thing, okay? But again, all governed by quantum physics. Now, how do you treat such little objects? Apparently my fingers are too large in order to take such a nanometer thing and put it from A to B and all this stuff. So a number of sophisticated techniques. I'm not going to go into that in detail, but bottom line, it looks a little bit like that the larger the object, the smaller the object, the larger the machine needs to be in order to be able to move it from A to B or to do something with that. This here is a transmission electron microscope, for example, so which means you basically shoot your electrons through your nanoscopic object, and then you look how the electrons are scattered, and from that you can construct images. You can do that with helium ions also. There, again, you don't shoot through it, but you reflect it. There are many other things. Here what you see is basically a chip. Okay, this length here is about, 1 centimeter. Here, this black thing in the middle is just a substrate of silicon. And somewhere in, what unfortunately you cannot see, somewhere here in the center, there's a single nanotube which was electrically contacted and with which we have performed electrical measurements in magnetic fields, for example, in electric fields, or we expose it to light and see what is happening, and so forth. And there's also the opportunity in the undergraduate curriculum to get hands-on experience on such top-class tools in your fourth year 3-month research projects, and of course in your summer student projects. Now, have a look, check it out. There's the physics webpage again for the Institute of Nanotechnology, or the Center for Research on Adaptive Nanostructures and Nanodevices, simply cran.tcd.ie. And there's also an initiative by the government which is called Inspire in order to promote nanoscience and nanotechnology, physics, of course, in Ireland. And one thing also I would like to invite you to have a look at, the Institute of Physics has recently launched a little booklet which you can get at the physics stand here in this building. So you go one floor down and then from here where I stand to the right, which gives you a few ideas about what you can do once you have studied physics. Not everybody ends up, of course, working in the university. Of course, you have the classical one, you can become teacher. But there are many, many, many other things, starting from being in banking, insurances, up to some medical applications. So there's a huge, huge range which opens in terms of job perspectives once you have gone through studying physics. So in the end, size matters in a way, and if you have any more questions or details, here's my email, just drop me one, or just write to the School of Physics at physics@tcd.ie. Thanks for your attention.